In the heart of Scorpius shines a giant unlike any other Antares A, a fiery red supergiant so vast it dwarfs our sun. Its glow has guided ancient civilizations and still dominates the night sky today. Tonight we explore the true scale and mystery of this stellar titan. If you enjoy the journey, please like, subscribe and share, and tell us in the comments what surprises you most about stars this enormous. Thank you for watching. Now let's begin. Far from the solar system, the Milky Way stands as a wide rotating disk of stars, gas and dust wrapped around a dense central region. And from this broad structure, the part of the sky that holds the constellation, Scorpius is only one small patch in a much larger pattern. The disk stretches for tens of thousands of light-years thin compared with its width, and it is laced with spiral arms in which stars form age and drift. The Sun orbits within one of these arms a little more than halfway from the galactic centre to the outer edge, so that the night sky from Earth is filled not by a uniform scattering of stars, but by a thick band where the line of sight runs along the crowded plane of the disk. To people on Earth, this band appears as a faint milky glow arching across the sky on dark nights, a soft merging of countless unresolved stars. In some directions the band is pale and delicate, in others it is dense and knotted with darker streaks, where cold clouds of dust block the light behind them. Toward the constellations of Scorpius and Sagittarius, the band is especially rich because in that direction the line of sight passes near the galactic centre and through some of the most crowded inner regions of the disk. Here the Milky Way thickens into a broad swath that climbs up from the horizon, slopes across the sky and sinks again its brightness, modulated by irregular lanes of dust that carve sinuous shapes through the light. Within this band, the individual stars resolve into a complex mixture of colours and types. There are cool red and orange giants whose outer layers have swelled and cooled hotter, white and blue stars whose light pierces the haze more sharply, and clusters where groups of young stars gather together as subtle knots against the background. The light from all of them adds layer upon layer to the pale glow of the Milky Way, so that the sky in this region looks thicker and deeper than in directions away from the galactic plane. The disk above Scorpius is not smooth. Bright star clouds sit beside dark voids where interstellar dust has gathered into long twisting structures. These dark rifts do not mark empty space, but rather dense cold material that absorbs visible light from the stars behind and re-radiates energy at longer wavelengths that human eyes cannot see. Between the rifts lie star fields so crowded that even modest telescopes reveal dense sprays of points, each one a sun in its own right. On a clear night far from artificial light, the part of the Milky Way that crosses the region of Scorpius casts a soft presence that can be seen even with peripheral vision, a luminous path that is brightest high in the sky when the inner Milky Way faces the night side of Earth. The disk that gives rise to this view is in constant motion. Stars orbit the galactic centre over hundreds of millions of years. Clouds of gas drift and are compressed. New stars ignite, and old stars move off the main plane as gravity and time reshape their paths. From moment to moment in a human lifetime, however, the pattern seems almost fixed. The same broad band rises and sets with the seasons slowly shifting, earlier or later in the night, as Earth moves around the Sun but keeping its recognizable sweep across the constellations. In the region where Scorpius lies, this band passes near the direction of the galactic centre, so that behind the visible stars and dust there is a bright bulge of unresolved light from many more distant stars crowding the inner galaxy. Although that bulge itself is hidden by intervening dust in visible light, Its presence is hinted at by the thickness and brightness of the Milky Way in this part of the sky. Within this crowded zone, the disk seen above Scorpius contains stars at many different distances. Some are relatively nearby members of local associations and moving groups. Others reside far deeper in the galaxy, their light dimmed and reddened by the dust they traverse. Each point of light is shaped by its own history of formation and evolution, yet from Earth they merge into patterns defined by chance alignment along the line of sight. Among these patterns, one reddish point stands out by being both bright and distinctly coloured, a star that draws the eye naturally when this part of the sky is visible. It shines against the mottled background of the Milky Way band, its light also affected by the dust and gas that fill the disk, but still luminous enough to mark a clear focal point within the broader galactic glow. The Milky Way disk surrounding this point is the structural stage upon which the star appears, a framework of spiral arms, dust clouds and star fields that together create the backdrop for the bright heart of the constellation that will be described in more detail at smaller scales. For now, at the scale of the galaxy, Antares is one of many luminous stars embedded in the wide and slowly rotating disk, part of a complex layered structure whose full extent far exceeds the single segment visible above Scorpius on any given night. The band that crosses this part of the sky is a cross-section through that structure where stellar orbits, interstellar material, and the position of the Sun combine to present a particularly dense and intricate view of the Milky Way disk. Within the broad glow of the Milky Way, the constellation Scorpius appears as a distinct pattern of stars that many cultures have likened to the form of a scorpion, and this pattern provides the next step inward from the galactic scale to the more local geometry of the night sky. When the skies are dark and clear, the constellation occupies a region near the central bulge of the Milky Way, low in the southern sky for many northern observers, and high overhead for observers closer to the equator and in the southern hemisphere. Its stars trace a shape that is unusually curved and segmented compared with many other constellations, which helps it stand out even against the crowded backdrop of the inner galaxy. Near the middle of this pattern lies a bright reddish star that functions as the heart of the scorpion figure, while a line of stars arcs downward and then hooks back upward to form a tail that ends in a sharper pair of points often associated with the stinger. Above the heart, other stars form the head and upper body. Together, these points make a pattern that many people find easier to recognize than the uneven stick figures of some neighboring constellations, and this helps fix Antares in the mind as part of a coherent sky shape rather than as an isolated light. These stars of Scorpius are not all at the same distance yet. From Earth they blend into a two-dimensional design. Some are relatively nearby members of stellar groupings associated with the Scorpius-Centaurus region, while others lie much farther into the galaxy, their light filtered by intervening dust in the Milky Way. Still, the human eye tends to link stars by apparent brightness and proximity on the sky, so the scorpion figure emerges from these chance alignments of unrelated objects. Antares stands out immediately in this figure because of both brightness and colour. Most of the bright stars along the tail and body appear white or bluish, but Antares shines with a pronounced orange-red hue. This colour arises because it is a cool, swollen star whose surface is significantly cooler than that of hot blue stars, so that it radiates more strongly at longer wavelengths that the human eye perceives as red. Interstellar dust along the line of sight likely contributes some additional reddening, but even when this effect is accounted for, the star remains intrinsically cool and luminous. To a careful observer, its reddish glow gives the scorpion a kind of focal centre. Many of the stars that trace the tail and claws have relatively similar brightness, yet none of them match the combination of intensity and deep colour that Antares displays. The contrast between the red heart and the paler neighbours makes the constellation easier to pick out against the blended background of the Milky Way band. Scorpius occupies a particular position relative to the path that the Sun appears to take through the sky over the course of a year. This apparent path, called the ecliptic, crosses the body of the Scorpion near Antares, so that the Sun, Moon and planets sometimes pass through or near the constellation. When the Moon moves close to Antares, its own brightness can overwhelm many of the surrounding stars, but the reddish heart often remains visible, even against the lunar glare when the separation is not too small. Bright planets such as Mars or Jupiter sometimes visit this region as well, creating striking groupings when they appear near the curving line of the tail or the central star. Mars in particular can sometimes echo the colour of Antares, and their temporary proximity on the sky has attracted attention since antiquity. The seasonal visibility of Scorpius helps define when Antares is best seen. In the northern hemisphere, the constellation is most prominent in late spring and summer evenings, when it rises above the southeastern horizon and moves across the southern sky before setting in the southwest. In the southern hemisphere, it appears higher in the sky and can dominate winter nights with the tail sweeping overhead and the heart glowing strongly in a darker, more vertical segment of the Milky Way band. As Earth moves in its orbit, the timing of these appearances shifts, but the basic pattern of seasonal prominence remains. When Scorpius is near the Sun in the sky, it becomes hidden in daytime glare and is not visible at night, but half a year later it returns rising earlier and earlier until it reaches a period of peak visibility at convenient evening hours. The interplay between the constellation and the background Milky Way enhances the impression of depth in this part of the sky. The tail runs along a thick mottled zone of star clouds and dark dust lanes, while the head and upper body approach regions where the Milky Way band begins to thin out. Antares sits near a point where bright star fields and darker patches meet its light backlit by the broader galactic glow. In long exposure images, this region reveals complex structures of bright and dark nebulosity, yet even to the unaided eye the area can seem richer and more textured than many other patches of sky, especially under very dark conditions. Scorpius does not stand alone in this region. Nearby constellations such as Sagittarius Libra and Ophiuchus share the same stretch of the Milky Way, and the boundaries between them are defined by convention rather than by physical separations. Nevertheless, Scorpius is one of the few constellations whose outline still resembles the creature or symbol with which it is traditionally associated. Many patterns in the sky require imagination to map from stars to names, but here the sinuous body claws and curved tail display a shape that many observers recognize once it is pointed out. This recognizable outline makes Antares easier to locate because one can trace the curve of the tail and the placement of the claws and find the red star marking the center of the body. At the scale of human perception, then Antares functions as a key anchor point within the broader skeleton of the constellation. The arrangement of the stars of Scorpius is a projection of three-dimensional galactic structure onto the celestial sphere, and the visibility of the pattern depends on Earth's specific vantage point within the Milky Way. From another star system, the alignment would be different, and the Scorpion would likely dissolve into an unremarkable scattering. From Earth, however, the combination of a bright red central star, a gracefully curving tail, and a location embedded in a rich segment of the Milky Way creates a distinctive feature of the sky. Within this feature, Antares marks the heart of the Scorpion, a role defined not by physical connection to the neighbouring stars but by the geometry of the line of sight, and by the way the human eye picks out colour and brightness against the dense galactic background. In this way, the constellation context frames Antares as more than an isolated light, anchoring it within a recognizable figure that emerges directly from the structure of the Milky Way disk already described at the larger scale. Beyond the apparent flatness of the constellation pattern, the stars that make up Scorpius occupy a particular region of the Milky Way's spiral structure, and among these the group known as Upper Scorpius stands out as a concentration of relatively young stars gathered within a nearby segment of the galactic disk. The Sun resides in a modest spiral feature often called the local arm or local spur, a lane of stars, gas and dust that runs between the larger neighbouring arms. Within this feature lie several loose associations of young stellar groups, and the Scorpius-Centaurus association is one of the closest and most studied. Upper Scorpius forms one part of this broader complexer region, where not so long ago in astronomical terms a cloud of cold gas condensed fragmented, and gave rise to a generation of predominantly massive and intermediate mass stars. Seen from Earth, these stars happen to project into the area marked by the constellation Scorpius, so that when observers look toward the curved tail and body, they are gazing along a line of sight that threads through this young association. Like many star-forming regions, Upper Scorpius does not appear as a tight spherical cluster, but rather as a loose collection slightly elongated and spread out, because the stars that formed there have already begun to drift apart under their own motions and under the influence of the galaxy's gravity. The distances to individual members differ slightly, yet they cluster within a band of a few hundred light-years, around a characteristic value placing them relatively close on the galactic scale. This proximity is one reason the association has been examined carefully using many observing methods. It offers a kind of local laboratory in which astronomers can study how massive stars form, evolve and interact with their environment over a few tens of millions of years. Within Upper Scorpius, many of the brightest members are hot blue stars of spectral types associated with high masses and short lifetimes. These stars shine with intense ultraviolet radiation and powerful stellar winds that sculpt the surrounding interstellar medium. Over time, their energy output can erode the remnants of the original birth cloud, driving shock fronts outward and compressing more distant gas into knots that may in turn form new stars. Some of the more massive stars born in the earliest phases of the association have likely already ended their lives as supernovae, sending expanding shells of debris into the region and enriching it with heavier elements. Evidence for such events appears in the form of large cavities and bubbles in the gas around the Scorpius-Centaurus association, as well as in the motions of the stars themselves, which suggest past episodes of energetic feedback that helped clear out the environment. The association's different subgroups, including Upper Scorpius, show slight differences in age, with Upper Scorpius often characterized as one of the younger components, containing stars that have had time to evolve off the main sequence if they were born with sufficient mass, but not yet enough time to disperse completely. In this context, Antares sits as a luminous and evolved member within or near the Upper Scorpius subgroup, a red supergiant that marks the endpoint of evolution for a massive star that once shone as a hot blue object similar to some of its neighbours. The fact that such a star now exists among the association's members offers clues to the timing of star formation in the region, since a star of this mass and stage of evolution can only remain in such a dramatically expanded state for a relatively short fraction of its overall life. Its presence indicates that the burst of star formation that produced Upper Scorpius is no longer in its earliest phases, and that some of its most massive children have already advanced into late evolutionary stages. Around these massive stars, including the one that becomes the focus of later sections, there are many lower mass stars that formed from the same original clouds. These stars with masses closer to or below that of the Sun evolve far more slowly, and still appear as ordinary main sequence stars or as young pre-main sequence objects. Some retain disks of gas and dust where planets may be forming or have already formed. Together, the mix of hot luminous stars and more numerous fainter companions gives Upper Scorpius a layered structure in both brightness and mass. Observationally, the association is recognized through measurements of stellar motions and distances. Stars that share similar space velocities and lie at comparable distances are likely to have a common origin. By tracing these motions back in time, astronomers can infer when the group was more compact and where in the galaxy the parent cloud might have been located. For Scorpius Centaurus and its subgroups, these reconstructions suggest that star formation proceeded in stages with different regions, igniting at slightly different times. Upper Scorpius represents one such stage, and its current configuration reflects millions of years of gravitational evolution. From the vantage point of Earth, however, these dynamic details are hidden behind the almost static appearance of the night sky. The stars of Upper Scorpius drift too slowly to reveal their motions to the unaided eye over a human lifetime. What can be noticed is the concentration of bright stars in the body of Scorpius and near neighbouring constellations, a sign of the underlying association. Within the curved line of the Scorpion's body and the region immediately around it, many of the visible stars belong to this cohesive structure, even though they are separated by many light years and are moving through space along slightly diverging paths. The local spiral arm segment that contains Upper Scorpius also hosts other associations and clusters, some older and more dispersed, others younger and still embedded in their natal gas. Interactions between these groups and between the stars and the interstellar medium gradually reshape the environment. Shock fronts from older associations can compress gas clouds that then form newer generations of stars in a chain of events that spans tens of millions of years. The Scorpius-Centaurus association, including Upper Scorpius, appears to be part of such a sequence in the local arm, a snapshot in a longer history of star formation waves that sweep through the galaxy's spiral structure. Antares draws particular attention within this larger pattern, because its evolved state makes it both brighter and redder than many of its siblings, setting it apart visually, while still tying it to the shared origin of the group. From the perspective of the galaxy, Upper Scorpius is only a small knot of enhanced star density within one part of a single spiral arm. From the perspective of observers on Earth, it forms a key part of the scenery behind the constellation, Scorpius giving the region a rich population of young and middle-aged stars and providing the immediate stellar neighbourhood in which the red supergiant at the heart of the constellation resides. The association and its place in the local spiral arm thus supply the intermediate scale context for Antares, bridging the gap between the grand structure of the Milky Way described earlier and the more tightly focused view of the individual star and its close companions that will follow at smaller scales. The Scorpius-Centaurus association often shortened in technical discussions, but here considered in full forms a wide and loosely bound family of young stars spread across a large stretch of the local spiral arm, and it provides the broader stellar environment that surrounds the more compact Upper Scorpius region already described. Rather than being a single dense cluster like some famous young groups, this association resembles a sprawling complex whose members share a common origin in giant molecular clouds that once occupied this part of the Milky Way. Over time, those cold clouds fragmented and collapsed in different places and at slightly different epochs, giving rise to several related subgroups that now cover a large area on the sky. Among these Upper Scorpius, Upper Centaurus Lupus, and Lower Centaurus Crux are often distinguished by their average ages, positions, and characteristic motions through space, yet all belong to the same extended star-forming event that unfolded over tens of millions of years. The association stretches across a broad swathe of the southern sky, overlapping the constellations Scorpius, Lupus Centaurus, and surrounding regions, and from Earth it appears as a subtle enhancement in the number of bright hot stars sprinkled along this part of the Milky Way band. Astronomers recognize its members not by visual grouping alone, but by careful measurements of proper motion, radial velocity and distance, which together reveal that many of these stars move in related streams and lie at comparable distances, as if they were fragments of an earlier, more compact configuration that has since expanded. In the earlier life of the association, the parent clouds of gas and dust were thick, cold structures, extending over hundreds of light years with knots and filaments, where density fluctuations grew under gravity. In those densest pockets, star formation ignited, and as the first massive stars turned on their radiation and stellar winds began to erode the surrounding material, over several million years, repeated episodes of star formation and feedback carved cavities in the gas-driving shells and bubbles outward. Supernova explosions from the most massive early members added their own energy, accelerating the clearing process and seeding the region with heavier elements formed in stellar interiors. Observations of large, low-density cavities and expanding shells of gas in and around the Scorpius-Centaurus association suggest that such events have taken place repeatedly, leaving behind a complex system of bubbles whose edges are traced by chains of young stars and glowing gas. The Sun itself sits near the boundary of one of these cavities, sometimes called a local bubble, and studies of its relation to the association indicate that past activity in Scorpius Centaurus may have helped shape the immediate interstellar environment around the solar system. Within this broader complex, the three main subgroups show a progression in age that hints at a sequence of star formation moving through the parent clouds. Lower Centaurus Crux, often regarded as the oldest of the three, contains stars that have had more time to drift apart and to evolve away from the hottest, youngest phases. Upper Centaurus Lupus appears somewhat younger, while Upper Scorpius is younger, still hosting stars that reveal a more recent burst of star formation. This age gradient suggests that one episode of star formation and feedback may have triggered subsequent episodes in neighboring regions as expanding shells compressed adjacent gas and induced further collapse. In this way, the entire association can be understood as the product of a cascading chain of events, in which one generation of stars influences the birth of the next. Antares belongs to this extended family embedded in or near the Upper Scorpius subgroup, and shares its origin in the gas that once filled this part of the galaxy. The fact that Antares has already evolved into a red supergiant while many association members remain on or near the main sequence underscores how differences in mass shape stellar lifetimes. A star born with several times the mass of the Sun consumes its nuclear fuel, much more rapidly moving through its phases of evolution in far less time than a lower mass sibling. Thus, in a group where the average age is measured in tens of millions of years, the most massive members can already appear as evolved giants or supergiants, while most lower mass stars still resemble the Sun at a much earlier stage of life, or even retain characteristics of youth such as disks and enhanced activity. The Scorpius-Centaurus association does not possess sharp boundaries in space. Its edges grade into the more diffuse background population of field stars, and its members intermingle with stars from other origins. Over time, gravitational tugs from the galaxy's mass distribution and from passing clouds and associations will further disperse its stars, mixing them into the general field so thoroughly that their shared history becomes harder to reconstruct. At present, however, their common motions still preserve the memory of their birth environment. Precise astrometric surveys that measure positions and motions with high accuracy allow astronomers to identify coherent groups within the broader field and to assign stars to the Scorpius-Centaurus association with increasing confidence. By tracing orbits backward in time, one can estimate when and where the subgroups were most compact, revealing a picture in which a once continuous complex of clouds and stars has stretched and thinned as it orbits the galaxy. The association's influence extends beyond the stars themselves. The feedback from massive members alters the physical state of the interstellar medium over large volumes. Gas in the vicinity may be heated, ionized, or pushed aside, and dust grains can be processed by strong radiation fields and shocks. These processes can create bright nebulae, where gas and dust are illuminated, as well as dark clouds, where material remains dense and shielded. The structure of nearby star-forming regions, such as dark clouds and reflection nebulae within and around this part of the Milky Way, bears the imprint of such interactions. Cavities traced in radio and X-ray observations and arcs of gas seen in emission outline the impact of winds and past supernova from association members. In all of this, the Scorpius-Centaurus association functions as a kind of regional engine of change, in the local spiral arm mediating the cycle in which gas collapses into stars is then reshaped by their energy output, and eventually returns enriched material to the interstellar medium. From the viewpoint of the night sky, however, these large-scale processes compress into patterns of bright points against the Milky Way. The association appears as an area rich in luminous stars, some arranged into familiar constellations and others scattered more diffusely. The human eye cannot distinguish which stars share a common birthplace, and which do not, but careful analysis reveals that many of the prominent stars in the southern sky belong to this extended family. Antares is one such star, its distinctive red light marking a particularly evolved member of the association. Around it, other bright stars trace the outlines of Scorpius and nearby constellations, while still more fainter members fill the background. Together they form the stellar context within which the red supergiant resides, an environment shaped by previous generations of star formation and by the ongoing evolution of massive stars. At this scale, the association sets the stage on which the more immediate surroundings of Antares will appear, blending global star-forming history with the local grouping that has given rise to one of the most conspicuous red supergiants in the night sky. In the region of the Milky Way where Scorpius lies, the space surrounding Antares is threaded with clouds of gas and dust that form one of the most visually striking complexes in the nearby galaxy, and these interstellar structures provide the immediate backdrop against which the red supergiant shines. Rather than being empty, the space between the stars in this direction contains cold molecular clouds, warmer atomic gas, and fine dust grains that together shape how light travels from distant regions to the observer. Some parts of this material lie in front of Antares along the line of sight and dim or redden its light, while other parts lie near or behind the star and are illuminated by its radiation and by the light of neighbouring hot stars. The result is a patchwork of glowing and dark regions in which Antares appears embedded. In long exposure images, the area around the star reveals blue reflection, nebular yellow and orange patches where dust scatters and mixes the light from different stars, and darker lanes where denser material blocks light more effectively. One of the most studied features in this broader complex is a dark and bright region near the star Rho Ophiuchi, a nearby young stellar nursery where many new stars are forming inside dense clouds. Although the exact three-dimensional arrangement of these clouds and of Antares involves distances that differ by tens of light years, from Earth they overlap in projection, creating a scene where the red supergiant, the young stars of the nursery, and the swirls of dusty gas appear intertwined. Dust grains in these clouds are typically tiny, comparable in size to smoke particles, or smaller, and they interact with starlight in ways that depend on wavelength. Blue light is scattered more efficiently than red light, so when dust lies near bright hot stars it can reflect and scatter their blue-white light into surrounding space, forming reflection nebulae that take on a soft blue colour. At the same time, dust in front of stars along the line of sight preferentially removes blue light and lets more red light pass, making those stars look redder than they would if seen without intervening material. In the region around Antares, both effects are at work. Some dusty patches reflect the light of hot stars in the area, while other dust lanes and clouds lie between Earth and parts of the star field, deepening the overall reddish hue of the region. The glow around Antares itself includes contributions from the star's light scattered by nearby dust, which can take on a more yellowish or orange cast, where it mixes with other sources of illumination. Gas in the vicinity adds further structure. In regions where hydrogen and other elements are ionized by ultraviolet radiation from hot stars, emission nebulae can form shining with their own faint light, as electrons recombine with ions and drop to lower energy levels. These emission regions often appear as subtle red clouds or filaments in the optical range. In other places, gas remains mostly neutral, but is warmed by starlight or by passages of slow shock waves, contributing to diffuse glows that are less sharply defined. The combination of reflection, emission, and absorption creates a pattern of bright knots-coloured patches and dark voids around Antares and its neighbours. From Earth, the entire complex occupies a sizable patch of sky, large enough that it requires wide fields of view to capture in a single frame. In very dark conditions, unaided human vision can detect hints of the structure, as uneven brightness and slight colour variations around the region of Scorpius and its neighbouring constellations. But the full richness of the clouds emerges in photographs that accumulate light over long periods. These images reveal filaments that twist through the field, dense globules where new stars may be forming, and broad sheets of dust that drape across the background star fields. The clouds themselves move slowly over time, shaped by gravity turbulence and the collective effects of nearby stars, but on human timescales they appear almost fixed. Many of the features currently visible have persisted for millions of years, though their exact shapes evolve gradually as internal motions shift material. The presence of massive stars in the Scorpius-Centaurus association, including Antares and several hot blue stars, plays an important role in sculpting these clouds. Their radiation pushes on dust grains through the pressure of light, and their stellar winds and eventually their supernova explosions send shock waves into the interstellar medium. These processes can compress some parts of the clouds, leading to new star formation, while dispersing or eroding other parts, thinning them or sweeping them into arcs. The Rho Ophiuchi region, with its cluster of young stars embedded in dense material, may be one example of a site where such interactions have helped trigger or shape the current generation of star formation. Observations at wavelengths beyond visible light provide additional clues to the structure and physical conditions in these clouds. Infrared observations can peer through much of the dust that blocks visible light, revealing embedded stars and the warm glow of dust grains heated by starlight. Radio and millimeter measurements trace cold molecular gas, making it possible to map where dense clumps and filaments reside. X-ray observations can highlight regions where hot gas fills cavities carved by past energetic events. Together, these different views show that the clouds around Antares and the Rho Ophiuchi complex belong to a larger network of structures shaped over many millions of years by the cycle of star formation and feedback in the local spiral arm. At the distance of a few hundred light-years, the complex counts as one of the closest active star-forming regions to the Sun, which is why it has become a benchmark for studies of how stars and planetary systems form. From the standpoint of Antares, which resides in or near the same broad volume of space, these clouds represent the remnants and byproducts of earlier and ongoing episodes of star formation. Some of the material in them may share a common origin with the gas that once collapsed to form the red supergiant itself. Other portions may be the accumulated debris from older generations of massive stars whose winds and explosions enriched the area with heavier elements. At the scale considered here, the focus remains on the interstellar environment, rather than on the material directly expelled by Antares, which will be examined at a closer range in later stages. For now, the important point is that Antares does not shine in isolation. Its light passes through, reflects off and mingles with a complex three-dimensional tapestry of clouds and dust that fill the region of space around it. When observers look toward the heart of Scorpius, they see not only a bright red star but also the visible imprint of the surrounding structures which shape the colors, brightness patterns and textures of the sky. The gas and dust around Antares thus frame the star within a broader interstellar context, linking the individual supergiant to the ongoing processes of cloud evolution and star formation in this nearby corner of the Milky Way. Against the crowded backdrop of the Milky Way, and within the curved outline of Scorpius Antares itself stands out as a single, bright orange-red point that observers recognize as a red supergiant star at a distance of roughly 500 to 600 light-years from the Sun, even though the exact value remains uncertain within that range. To the unaided eye under dark skies, it appears as one of the brightest stars in the constellation, rivaling or surpassing many of its neighbours in intensity and drawing attention, because its light is distinctly warmer in colour than the cooler white or blue stars nearby. That colour is the first obvious clue to its physical nature. While hot compact stars radiate most strongly at shorter wavelengths and appear white or blue, white Antares radiates more strongly at longer wavelengths, giving it a deep orange-red hue that marks it as a cool, swollen star with an extended outer atmosphere. This colour difference is not only intrinsic. Interstellar dust along the line of sight also removes some of the bluer light, adding a modest extra reddening. But even when this effect is taken into account, the star remains inherently cool compared with many of its bright neighbours. Spectroscopic observations, which spread the star's light into a spectrum of colours and absorption features, classify Antares as a red supergiant of spectral type, around M1 to M1.5, in the supergiant class, indicating a surface temperature of only a few thousand degrees above absolute zero, significantly cooler than the surface of the Sun. The spectral lines show deep features associated with molecules and neutral atoms that form in a cool, extended atmosphere, and their shapes and strengths mark the star as highly luminous with a low surface gravity. This combination of low temperature and high luminosity implies a very large radius. Estimates based on interferometric measurements, which resolve the apparent size of the stellar disk on the sky, and on models of red supergiant atmospheres, suggest that the radius of Antares is several hundred times that of the Sun. The exact number varies from study to study because the outer layers of the star are not sharply defined, and because different observing wavelengths probe different depths in the atmosphere, but values on the order of a few hundred solar radii are common with some analyses pointing to even larger ranges. Similarly, the mass of Antares is not known with the precision possible for some less complex stars. Models of stellar evolution that aim to reproduce its luminosity, temperature, and evolutionary state generally place its mass in a broad range of roughly 10 to 20 times the mass of the Sun. This uncertainty reflects both observational challenges and the sensitivity of theoretical tracks to details of rotation, mass loss, and internal mixing, all of which can alter the path a massive star takes through its life. What can be said with confidence is that Antares began as a massive star significantly heavier than the Sun, and has reached a stage where its outer layers have expanded and cooled, while its core has advanced through multiple stages of nuclear fusion. From the standpoint of the sky, these physical properties translate into a star of remarkable brightness. Even at a distance of several hundred light-years, Antares shines as one of the brightest stars visible to the naked eye, with a luminosity tens of thousands of times that of the Sun when integrated over all wavelengths. Its brightness varies in a slow, irregular way, with modest changes in apparent magnitude over timescales of months to years. These variations reflect changes in the structure and temperature of the outer layers, including the influence of large convective cells and dynamic processes in the extended atmosphere. To human vision, these variations are subtle and not easily noticed without careful comparison, but photometric monitoring reveals a pattern of quasi-periodic and irregular changes that are characteristic of many red supergiants. The distance to Antares has been the subject of repeated study because accurate distance is essential for determining intrinsic luminosity and for constraining models of its mass and radius. Traditional methods based on ground-based parallax measurements were limited by the star's brightness, large apparent diameter, and complex atmosphere, all of which complicate the determination of its precise position on the sky. Space-based astrometry missions have improved the situation, providing parallax measurements with higher precision, yet even these are affected by the same complications. As a result, the distance is still quoted with some range typically in the neighborhood of 500 to 600 light-years rather than as a single, sharply defined value. This level of uncertainty is common for very bright extended stars and does not undermine the overall conclusion that Antares is both nearby in galactic terms and highly luminous. Observations across different parts of the electromagnetic spectrum deepen the picture of the star's nature as a red supergiant. In visible light, the orange-red color dominates. In the infrared, the star appears even brighter relative to many neighbors because its cool surface emits strongly at longer wavelengths. Infrared observations also reveal emission from warm dust in its vicinity, some of which may be material lost from the star itself. At radio and submillimeter wavelengths, emission from molecules in the extended atmosphere and surrounding gas offers clues about the composition and dynamics of these outer layers. Together, these multi-wavelength observations build a consistent picture of a massive star in an advanced evolutionary stage, shedding material and sustaining a complex extended atmosphere that reaches far from the photosphere. From the perspective of sky watchers, however, these complexities are compressed into the simple impression of a bright red star that anchors the heart of Scorpius. Its apparent size on the sky is still far too small to be resolved by ordinary telescopes, yet specialized interferometric instruments can detect that the star's disk is not a mathematical point, but has a measurable angular diameter. These observations show that Antares subtends an angle corresponding to a physical size hundreds of times larger than the radius of the Sun. Images reconstructed from interferometric data hint at irregularities on the surface, such as bright and dark patches that may be associated with giant convective cells or with inhomogeneities in the atmosphere. These surface features change over time, indicating that the outer layers of the star are highly dynamic. Despite such internal complexity, Antares maintains its role in the sky as a steady reference point for navigation and constellation patterns at human timescales. Its slow drift across the celestial sphere due to proper motion is too small to change its place in Scorpius noticeably over centuries, and its brightness, though variable, remains high enough that it continues to rank among the visually dominant stars. In this sense, the red supergiant serves both as an object of detailed astrophysical study and as a familiar landmark in the night sky. For the current layer of this exploration, Antares A is understood primarily through its observable properties as a luminous, cool, extended star at a moderate distance, whose color, brightness spectrum and angular size together mark it as one of the most prominent red supergiants visible from Earth. Its more intricate relationships with nearby stars and with its own close companion belong to the next inward scale, where the focus shifts from the star as a single point of light to its role within a small stellar system in the local neighborhood. Although Antares often appears to the casual observer as a single red point in the heart of Scorpius, it is in fact part of a binary system in which a hot compact B-type star orbits the swollen red supergiant primary at a projected distance of a few hundred astronomical units, forming a small stellar family within the larger upper Scorpius environment. The recognition that Antares is double came from careful observations that revealed a faint bluish companion close to the bright primary, a difficult task because the intense glare and extended atmosphere of the supergiant tend to hide fainter neighbors. Early visual observations under exceptional conditions, followed by spectroscopic and high-resolution imaging studies, confirmed that the companion is not merely a chance alignment, but is physically associated, sharing motion and distance with the primary in a bound orbit. On the sky, the two stars are separated by only a small angle, so small that resolving them requires instruments with significant magnifying power and good seeing, or modern techniques that compensate for atmospheric distortion. To the unaided eye, they merge into a single point, and even in many modest telescopes, the brightness contrast makes the companion hard to detect. In instruments that do resolve the pair, the primary appears as a bright orange-red star, while the secondary shows as a much fainter blue-white point nearby. This color contrast reflects the underlying physical differences between the two stars. The main component, Antares A, is a red supergiant with a cool, extended atmosphere and a radius hundreds of times larger than that of the Sun, radiating most strongly in red and infrared wavelengths. The companion, often labeled as a mid-B-type main sequence star, is far smaller in radius, but much hotter at its surface, with a temperature several times higher than that of the primary. Its intense ultraviolet and blue light mark it as a star that is still in a relatively early stable phase of hydrogen fusion in its core, unlike the evolved giant it orbits. Because the two stars formed from the same original cloud of gas and dust, they are thought to be of similar age, yet their different masses have driven them along very different evolutionary paths. Antares A, born with significantly more mass than the Sun, has already exhausted hydrogen in its core and expanded into the red supergiant phase, while the B-type companion, somewhat less massive, has not yet completed its main sequence lifetime. This contrast between a highly evolved primary and a still main sequence secondary is a common pattern in binaries where the initial masses differed by a modest factor, and it allows astronomers to use the companion as an approximate reference for the age of the system. If the secondary remains on the main sequence, its mass and present state can constrain how long ago the pair formed, which in turn helps refine estimates of how quickly the more massive primary has evolved. The orbit of the Antares pair is wide and slow, At a distance of a few hundred astronomical units, even a massive binary requires many centuries or longer to complete a single revolution, and only a small segment of that orbit has been sampled by modern observations. Measurements of relative positions over decades reveal some motion, but the full path is not yet mapped out with precision. As a result, the exact orbital period, eccentricity, and orientation in three-dimensional space are still subject to significant uncertainty. Estimates typically place the period in the range of many hundreds to roughly a few thousand years, but these values should be regarded as approximate, constrained by the observed separation and the likely total system mass rather than by direct tracking of a full orbit. What is clear is that the two stars are gravitationally bound and share a common motion through space as part of the larger association. At the scale of the binary system, their mutual gravity defines a region within which objects would orbit them both, rather than drifting freely through the upper Scorpius environment. If there are any planets or smaller bodies associated with the Antares system, their orbits would have to fit within the gravitational framework set by the masses and separation of the two stars, but current observations do not provide direct evidence of such bodies around either component. Instead, the focus of study has been on the stars themselves, whose contrasting properties offer insight into both massive star evolution and the dynamics of binary systems. Spectroscopic observations play a key role in separating the contributions of the two stars. When light from the system is dispersed into a spectrum, the red supergiant primary dominates in the visible and infrared, with deep molecular bands and features characteristic of a cool, low-gravity atmosphere. Superimposed on or distinct from these features are the sharp lines and continuum of the hot B-type secondary, especially at shorter wavelengths, where the companion contributes a larger fraction of the total light. By modelling these combined spectra, astronomers can estimate the temperatures, surface gravities, and luminosities of both stars, and thereby infer their approximate masses and evolutionary states. The presence of the companion also provides a valuable reference point for calibrating some measurements of the primary. Because the secondary is a relatively normal B-type star, its properties can be compared with those of similar stars in other systems, helping to anchor models of the Antares pair as a whole. For example, if the companion's luminosity and temperature are known, its distance inferred from binary association with Antares A must be consistent with parallax, and with the brightness observed providing a cross-check on distance estimates that does not rely solely on the complex atmosphere of the supergiant. Similarly, the motion of the companion relative to the primary can, in principle, yield information on the total mass of the system, although the long orbital period means that only limited constraints are available at present. Visually, the Antares system illustrates how stellar pairs of very different evolutionary stages can coexist in a single, gravitationally bound unit. The red supergiant shines with a diffuse warm glow, while the companion contributes a pinpoint of blue-white light. In small telescopes under steady skies, the companion can sometimes be glimpsed as a faint spark near the primary, testifying to the extremes of brightness and temperature that can occur within a single system. More advanced instruments such as optical interferometers and adaptive optics-equipped telescopes can separate the two more clearly and study them in greater detail, even in the presence of the extended atmosphere and circumstellar material of the primary. From the perspective of the broader stellar neighborhood, the Antares binary remains only one of many systems within Upper Scorpius and the Scorpius-Centaurus association, but its striking contrast of colors and states of evolution makes it a particularly informative example. The hot companion's radiation, while dwarfed in total visible brightness by the immense luminosity of the supergiant, still streams outward into the surrounding space, adding to the combined energy output of the system and subtly influencing nearby gas and dust. At this scale, the Antares pair can be seen as a small, self-contained entity, two stars of common origin and shared motion bound together by gravity, differing in mass and evolutionary stage, and together forming the immediate stellar system at the heart of the constellation. The two stars of the Antares system together fill their surroundings with light, creating a radiation field that extends outward into the nearby gas and dust, and quietly shapes the appearance and physical state of the space around them. Antares A, as a red supergiant, supplies an enormous luminosity spread mainly across red and infrared wavelengths, while the smaller B-type companion, though far less bright in visible light, adds a significant contribution of higher energy, ultraviolet and blue photons. Close to the stars, this combined radiation field is intense. Every surface layer of the red supergiant emits light, and because the star is so large, the total number of photons streaming away each second is vast despite the relatively low surface temperature. The hot secondary, with its compact radius and much higher temperature, adds a narrower but energetic stream of radiation that is particularly important for the ionization and heating of nearby gas. As the light travels outward, its intensity decreases with distance spreading over larger and larger spheres centered on the pair, yet even at distances of many hundreds or thousands of astronomical units, the radiation remains strong enough to alter the environments of any small bodies or diffuse material that happens to lie within reach. In the immediate neighborhood of the binary photons from both stars interact with atoms, molecules, and dust grains. Ultraviolet light from the companion can strip electrons from hydrogen and other elements, creating small zones of ionized gas, where the radiation is intense enough and the density of material is sufficient. In these zones, electrons recombine with ions and emit light at characteristic wavelengths, adding faint emission that blends into the broader glow of the surrounding interstellar medium. Around and beyond such regions, ultraviolet and visible light heat dust grains and molecular gas, raising their temperatures slightly and changing the balance of chemical reactions that can occur on and between them. In the language of astrophysics, this creates photon-dominated regions where the radiation field plays a central role in controlling temperature and chemistry. Though the structures in the Antares neighborhood are complex and do not form simple symmetric shells, dust grains, which are abundant in the larger cloud complexes around Scorpius, sit in this radiation field and scatter and absorb light according to their sizes and compositions. Close to Antares, where the red supergiant's output dominates dust, illuminated primarily by its warmer spectrum, can reflect a more yellowish or orange glow, especially where the scattered light mixes with direct starlight along the line of sight. In places where the hot companion's blue-white light falls on dust more directly, the scattered light can appear slightly bluer, although the companion's luminosity in visible wavelengths is much smaller than that of the primary, and its influence on large-scale color patterns is correspondingly modest. Further away, where light from many stars in the association also contributes, the local radiation field becomes a blend of multiple sources, and the dust responds by producing reflection nebulae whose colors record this mixture. Radiation pressure, the gentle push exerted by photons on matter, acts on dust grains as well. Each photon carries momentum, and when it is absorbed or scattered by a grain, a tiny impulse is imparted. For individual grains, the effect is extremely small, but over long time scales and across many grains, the combined influence can help move dust away from the brightest sources. In regions where gas and dust are loosely bound, such as the edges of nearby clouds, this pressure combined with stellar winds and gas pressure gradients can gradually sculpt the material into arcs, filaments, and cavities. The light from Antares and its companion therefore not only illuminates the surrounding medium, but also contributes to its slow rearrangement. Observationally, the influence of the Antares radiation field is most clearly seen in the way nearby dust glows and reflects. In optical images, a soft halo sometimes surrounds the star where light scattered by dust, close along the line of sight, creates a faint diffuse envelope. This halo merges outward into the more extended reflection and emission structures of the wider cloud complex described earlier, so that it is not always possible to draw a sharp boundary between the part of the glow dominated by Antares and the part shaped by other nearby stars. In the infrared, where dust warmed by starlight radiates its own energy, regions around Antares appear brighter than they would if the radiation field were weaker. Infrared observations can reveal arcs or irregular patches where dust temperatures are slightly elevated, hinting at where the combined flux from the binary system falls most strongly on nearby material. At radio and millimeter wavelengths, molecules in the gas respond to the radiation field by changing their excitation states, which in turn alters the strengths and shapes of spectral lines used to diagnose conditions in the region. In some cases, the presence of a strong radiation field can reduce the abundance of fragile molecules by breaking them apart, while in others, it can promote the formation of more complex species on grain surfaces. The net effect depends on the balance between radiation intensity, gas density, and shielding by dust and geometry. In the Antares neighborhood, the mixture of bright stars, dense and diffuse clouds, and varying distances produces a patchwork of conditions that are only partly understood from current observations. The geometry of the binary system itself also matters. Because the companion orbits at a large separation, its contribution to the radiation field is not uniform in all directions relative to the primary. A point in space that lies closer to the hot star than to the red supergiant can experience a relatively stronger ultraviolet flux, while another point aligned more directly with the primary may see a spectrum dominated by red and infrared light. Over the course of its long orbit, the companion slowly changes position, and the detailed distribution of radiation shifts accordingly. However, the orbital timescale is so long that on human timescales, and even on timescales of many generations of observation, the configuration appears almost static. The radiation field that researchers measure today is a snapshot of a slowly evolving pattern that reflects both the intrinsic properties of the stars and their current orbital phase. From a broader perspective, the Antares system contributes its share of photons to the overall radiation field of the upper Scorpius and Scorpius Centaurus environment. Massive stars elsewhere in the association also flood the region with ultraviolet and visible light, and together these sources maintain a level of ionization and heating in the surrounding interstellar medium that differs from that in more quiescent parts of the galaxy. Within this general field, the immediate surroundings of Antares represent a local enhancement, a place where one red supergiant and its hot companion dominate the illumination over a limited volume. Any gas or dust within that volume responds primarily to their combined output, whether by glowing softly by reflecting their light, or simply by adjusting its temperature and chemistry to the steady, continuous bath of photons. At this stage of the exploration, the focus remains on light traveling outward from the binary and on the ways that light shapes the nearby environment at scales larger than the star's own extended atmosphere. The radiation field presents an outward face of the system, a flow of energy that connects the stars to their surroundings and that links the detailed physics inside the stellar photospheres to the visible structures of the interstellar clouds in which the system is embedded. Around Antares, a matter does not simply sit still under the flow of light. Over long periods, the star steadily loses material in a slow but persistent stellar wind that carries gas away from its extended surface and builds a circumstellar envelope, a region of space filled with outflowing material that is no longer gravitationally bound in the same way as the gas deeper inside the star. In massive red supergiants like Antares, this stellar wind consists mainly of atoms and molecules lifted from the outer atmosphere and then accelerated outward, reaching velocities of tens of kilometers per second. Although this speed is modest compared with the high-velocity winds of some hot stars, the sheer amount of material involved over hundreds of thousands of years means that the star can shed a significant fraction of its mass before it reaches its final stages of evolution. The physical processes that drive the wind are complex and still the subject of active research. In simple terms, large convective cells in the star's outer layers combined with pulsations and shocks can push gas above the nominal surface where the density is lower and temperatures can drop enough for molecules and dust grains to form. Once dust condenses in these upper layers, radiation pressure from the star's intense light can push on the grains, which in turn drag the surrounding gas outward through collisions sustaining the outflow. As this material flows away, it creates a roughly spherical but often clumpy envelope around the star, extending over many times the stellar radius and blending gradually into the surrounding interstellar medium. The density in this envelope decreases with distance, so that near the star the gas is relatively dense and warm, while further out it becomes thinner and cooler. In observations at infrared and longer wavelengths, parts of this envelope reveal themselves through thermal emission from dust grains warmed by the star's radiation, while radio and millimeter observations trace molecules such as carbon monoxide and other species that survive in the cool expanding gas. These measurements allow astronomers to estimate the rate at which Antares loses mass-finding values that, though uncertain, indicate a steady removal of matter over long timescales. The circumstellar envelope around Antares is not smooth. High-resolution imaging from large telescopes has revealed that the outflow is structured with arcs, knots, and clumps of dust and gas rather than a uniform shell. These structures suggest that the mass loss is uneven in time and direction, perhaps influenced by giant convective cells on the stellar surface, by episodic events where more material is ejected, or by the subtle gravitational effects of the companion star. Some plumes appear as localized enhancements extending outward from the vicinity of the star along preferred directions, while other regions show thinner, more diffuse emission. Over time, these features drift outward, gradually merging into the more general envelope as they move away from the star and are smoothed by expansion. The slow but continuous expansion means that regions now far from the star were once much closer, containing gas that had only recently left the atmosphere. In this way, the circumstellar envelope preserves a record of past mass loss, with its inner zones reflecting more recent episodes, and its outer zones containing material ejected longer ago. The interface between the envelope and the surrounding interstellar medium is not sharp, but rather a broad region in which the density and velocity of the outflow gradually adjust to match those of the ambient gas. In this region, shocks can form where the wind encounters denser patches of interstellar material, or where older, slower wind interacts with more recent, faster outflow. Such interactions can enhance local densities and create additional structure in the envelope, contributing to the arcs and shells seen in some observations. The stellar wind from Antares also enriches its surroundings with elements created inside the star. The gas lifted from the outer layers contains heavier elements produced in previous stages of nuclear fusion and brought to the surface by convection and internal mixing. As this material moves outward and eventually mixes into the interstellar medium, it adds to the pool of gas from which future generations of stars and planets may form. In the case of Antares, which resides in a region already shaped by multiple generations of star formation in the Scorpius-Centaurus association, this enrichment is part of a continuing cycle in which massive stars return processed material to space. At the scale considered here, however, the focus remains on the geometry and dynamics of the circumstellar envelope rather than on the later fate of its material. From Earth, the envelope does not appear as a sharply defined object through ordinary telescopes. The bright glare of the star overwhelms most of the scattered light from nearby dust, and the gas itself is invisible in broad-band optical light. Only through specialized techniques such as high-resolution infrared imaging, interferometry, and spectroscopy does the extended structure become apparent. These observations show that Antares is surrounded by a halo of emission that reaches well beyond the photosphere, confirming that the star is actively shedding mass. When the system is viewed in certain infrared bands, the central bright point is accompanied by faint irregular patches that mark concentrations of warm dust, while in molecular line emission maps the gas appears as an expanding distribution with a characteristic velocity pattern. Together, these data reveal a picture in which the stellar wind streams outward, carrying with it clumps and filaments that trace the history of recent mass loss. The presence of the B-type companion star adds another layer of complexity to the circumstellar environment. Although the companion is distant enough that it does not directly strip material from the supergiant surface in the way close binary companions sometimes do its gravity, and radiation can still influence the flow of gas and dust on larger scales. For example, as the wind expands into the region where the companion orbits, the secondary's gravity may slightly focus or deflect the outflow, creating asymmetries in the envelope. The companion's ultraviolet radiation can also ionize portions of the gas in the outer envelope, especially on the side facing the hot star, altering its temperature and ionization state compared with regions shielded from this radiation. However, the overall mass loss is dominated by the processes in the red supergiant's own outer layers, and the circumstellar envelope can be understood primarily as the product of the star's internal dynamics and radiation acting on its outer atmosphere. In the context of the wider interstellar environment described earlier, the envelope of Antares represents a local star-centered structure, superimposed on the larger cloud complex, while the broader clouds contain material from many sources and are shaped by the collective influence of multiple stars. The circumstellar envelope is directly tied to one star and its ongoing evolution. It constitutes the immediate zone in which the star's mass loss reshapes space, filling it with slowly moving gas and dust that will eventually drift beyond the near neighborhood and blend into the surrounding medium. At this stage of the journey inward, the focus rests on this extended outflowing layer, the bridge between the diffuse interstellar environment and the more tightly bound atmosphere of Antares A, which will be examined at the next level of detail. Within the circumstellar envelope around Antares A, the material carried outward by the stellar wind does not form a smooth, uniform shell, but instead gathers into clumpy dust clouds and irregular outflow structures that give the near environment of the star a markedly uneven appearance when observed with sufficiently high resolution. Close to the star, where gas first leaves the extended atmosphere, the densities and temperatures vary across the surface because of large convective cells and dynamic processes in the outer layers. These variations mean that some regions lift material more efficiently than others, so that the initial outflow is already patchy. As the gas expands and cools, dust grains form more readily in some patches than in others, depending on local density, temperature, and composition. Once dust condenses, radiation pressure from the luminous star pushes on the grains, and the grains in turn drag the gas, accelerating clumps of material away from the star. The result is an outflow in which certain directions become enriched with dense, dusty knots and arcs, while other directions contain only more diffuse gas. Observations with large ground-based telescopes equipped with high-resolution infrared cameras and interferometers have revealed these structures as bright or dark patches of emission in the near environment of Antares. At distances of only a few to perhaps a few tens of stellar radii from the photosphere, images show asymmetries where the brightness differs around the star, indicating that the distribution of dust and warm gas is far from spherical. In some directions, elongated plumes seem to extend outward, suggesting episodes in which a particular region on the star surface ejected more material, or in which large-scale flows carried gas preferentially along certain paths. In other directions, the emission appears more sparse, implying that less dust has formed there or that the wind is weaker. These clumps and arcs move outward at velocities of tens of kilometers per second, as measured by Doppler shifts of spectral lines from molecules in the outflow, and by changes in their positions over time in repeated images. Over intervals of several years, astronomers have been able to track the motion of individual knots of dust, watching them drift away from the star and gradually fade as they expand and cool. The fact that these features can be followed at all underscores how close and large Antares is on the sky. In many other red supergiants, similar processes likely occur but at greater distances, or with smaller apparent sizes that make them harder to resolve. In the case of Antares, the combination of proximity and angular diameter allows current instruments to probe the outflowing material with unusual clarity. The clumpiness of the outflow carries important implications for the way mass loss proceeds. Rather than being a steady uniform breeze that removes mass evenly in all directions, the wind behaves more like a sequence of overlapping bursts and flows, with some regions of the star contributing more strongly at certain times. Over long periods, this still produces an overall envelope that appears roughly spherical when averaged over many years and large distances, but on shorter timescales and smaller scales, the structure is markedly inhomogeneous. This inhomogeneity affects how the gas cools, how molecules form, and how dust grains grow and interact. Dense clumps can shield their interiors from the strongest radiation, allowing more complex molecules to survive or form, while more diffuse regions remain more exposed. The presence of clumpy structures also influences how the wind interacts with the surrounding interstellar medium. As the knots and arcs move outward, they eventually encounter the ambient gas that fills the larger cloud complex around Scorpius. In some directions, dense clumps may create small bow shocks as they plow into slower-moving material compressing gas and dust ahead of them. In other directions, more diffuse outflow merges gently into the environment, contributing mass without strong local disturbances. Over time, these interactions blur the distinction between material that originated in the star and material that was already present in the interstellar medium, gradually mixing them into a common pool. The B-type companion in the Antares system introduces additional asymmetries into the distribution of dust and gas, especially at larger distances where the companion's gravity and radiation exert more influence. As the outflow expands into the region where the companion orbits its presence, can modulate the flow, slightly enhancing densities in some directions and thinning them in others. For example, material moving along the line connecting the two stars may be slowed or focused by gravity, while gas moving in other directions may continue outward more freely. The companion's ultraviolet light can ionize the outer layers of some clumps, creating thin, ionized skins around otherwise neutral cores. These effects do not dominate the overall mass loss, but they add subtle structure to the outer part of the envelope, contributing to the arcs and brightness variations seen in detailed images Different observing wavelengths highlight different aspects of the clumpy outflow. In near-infrared images, warm dust close to the star glows brightly, outlining the inner portions of plumes and knots. At mid-infrared wavelengths, slightly cooler dust farther out becomes more prominent, revealing arcs and clumps at larger radii. In the millimeter range, emission from molecules such as carbon monoxide traces cooler, more extended gas, often showing a more uniform overall shape, but still bearing hints of asymmetry. By comparing images at multiple wavelengths and at different epochs, astronomers can build a three-dimensional and time-dependent picture of how the outflow evolves. For Antares, such studies have confirmed that the mass loss rate can fluctuate, and that certain directions show persistently enhanced flow, perhaps linked to enduring features in the stellar convection pattern or to rotational effects. The physical scale of the clumps and arcs is large when measured in everyday terms. A single dusty knot that appears as a faint patch near the star may span several astronomical units, or more comparable to or larger than the size of the orbit of Jupiter in the solar system. Yet in the context of the star's extended atmosphere and envelope, these structures are relatively small, just one part of a much larger and more diffuse flow. As they move outward, they expand and lose contrast against the background, eventually becoming part of the smoother envelope, and then part of the general interstellar medium. In this way, the detailed internal structure of the outflow close to the star gradually fades, leaving only broader shells and enhancements at larger distances. The clumpy nature of the outflow also matters for how efficiently dust forms and survives. In dense clumps, dust grains can grow by accreting material from the gas, while in more tenuous regions they may be more exposed to destruction by shocks or by energetic photons. The overall dust content of the envelope and the size distribution of grains within it affects how the circumstellar material interacts with light, determining the brightness and color of scattered light halos and the strength of infrared emission. Because Antares is bright and relatively nearby, measurements of its dust emission help refine models of red supergiant dust formation and mass loss, which in turn inform understanding of how such stars enrich galaxies with dust. At the scale considered here, however, the emphasis remains on the qualitative fact that the outflow from Antares A is structured into clumps, arcs, and plumes rather than being perfectly smooth. These features reveal the underlying irregularities in the star's outer layers and in the processes that lift material into space. They demonstrate that even in the apparently gentle, steady glow of a red supergiant complex, time-dependent flows are constantly reshaping the immediate surroundings, building a circumstellar environment that is rich in detail and history. Seen as a whole, the clumpy dust clouds and outflow structures around Antares form a textured shell within the larger circumstellar envelope, mediating between the deep interior processes that drive mass loss and the broader interstellar medium that will ultimately receive the star's expelled material. Just above the visible surface of Antares A, the atmosphere does not end abruptly, but extends outward through a series of layers where temperature, density, and composition change, gradually forming an extended atmosphere that reaches far beyond the radius that would be defined for a simpler, more compact star, and within this region, molecules and dust begin to appear in ways that are very different from the conditions around a star like the Sun. In massive red supergiants, the photosphere, which is the layer from which most visible light escapes, is only one part of a much thicker outer envelope of gas. Above it, gas remains partially bound by gravity, but is stirred by large-scale motions, shocks, and waves that arise from the vigorous convection and pulsations in the layers beneath. In Antares, these processes lift material to heights, where the gas becomes cooler and more rarefied, allowing molecules that cannot survive in hotter environments to form and persist. Observations at high spectral resolution and with interferometric imaging show that the star is not a sharply edged disk, but rather that its apparent size changes depending on the wavelength at which it is observed. At wavelengths where molecules absorb or emit strongly, the measured diameter of Antares can appear significantly larger than at wavelengths where the gas is more transparent. This behavior indicates that distinct molecular layers sit above the photosphere, contributing their own absorption and emission signatures and effectively enlarging the star at those wavelengths. These layers are sometimes referred to as a molecular atmosphere or molecular sphere, emphasizing that they represent a region where molecules such as carbon monoxide, water, and other species are abundant compared with the deeper, hotter layers. In these outer zones, temperatures fall to values where such molecules can form, yet the gas is still dense enough for collisions to sustain them and for radiative processes to produce strong spectral lines. The presence of these molecular layers means that the transition from the dense photosphere to the more diffuse circumstellar envelope is gradual and structured rather than abrupt. Gas lifted by convection and pulsation can overshoot the photosphere, rising into regions where pressure and temperature conditions differ enough to alter its composition and opacity, before either falling back or being accelerated further outward into the stellar wind. As a result, the extended atmosphere around Antares contains a mix of upflowing and downflowing material with complex velocity patterns superimposed on the general outward motion of the wind. Spectroscopic measurements reveal this complexity through subtle shifts and asymmetries in molecular lines, which can indicate gas moving at different speeds along the line of sight in different parts of the atmosphere. Interferometric imaging adds spatial information, showing that the brightness and apparent size vary across the stellar disk, and with wavelength consistent with large convective cells and inhomogeneous molecular layers. In some images, bright regions appear on one side of the disk, while darker regions mark where cooler gas or thicker molecular layers absorb more strongly. These patterns change over time, implying that the extended atmosphere is highly dynamic. The physical distances involved in this region are large in stellar terms. The extended atmosphere can reach out to several times the radius of the photosphere, so that what might be considered the edge of the star in visible light is only the inner boundary of a much larger envelope of partially bound gas. Within this volume, temperatures may range from values near those of the photosphere down to cooler regimes where molecules form and where dust grains can begin to condense in the densest and coolest pockets. However, not every part of the extended atmosphere reaches conditions suitable for dust formation, and the exact locations where dust appears depend sensitively on local density, temperature, and radiation. In Antares, as in other red supergiants, the extended atmosphere therefore serves as the immediate reservoir from which the stellar wind draws its material. Gas that is lifted high enough and cooled sufficiently can become part of the outflow, while gas that does not reach escape velocities may fall back toward deeper layers, contributing to a cycle of rising and sinking motions. This cycle further stirs the atmosphere and can generate shocks that propagate outward, compressing material in some regions and creating temporary density enhancements. Such shocks may help drive the mass loss by pushing material beyond the point where it can no longer be held by gravity alone. In the molecular layers, radiation interacts with the gas in complex ways. Molecules absorb and emit at specific wavelengths, shaping the emergent spectrum and affecting how energy is transported through the atmosphere. Some transitions can be pumped by the intense radiation field from deeper layers, leading to population inversions, and under some conditions mass emission in certain lines, although the strength and prevalence of such phenomena in Antares specifically remain subjects of detailed study. More generally, the molecular opacity alters how heat escapes, influencing the temperature structure and contributing to the extension of the atmosphere. Because molecules are sensitive to both temperature and density, their spectral signatures provide powerful diagnostics. By observing lines from different species and at different wavelengths, astronomers can infer temperatures, densities, and velocities at various heights in the atmosphere, building models that describe how the gas behaves between the photosphere and the onset of the freely flowing wind. These models must account for the fact that the atmosphere is not spherical and static, but three-dimensional and time-dependent, with regions of rising and falling gas, varying molecular abundances, and localized heating and cooling. The extended atmosphere is also where the first stages of dust formation begin. In the coolest, densest pockets, atoms can stick together on tiny seed particles, gradually forming grains. These grains may initially be small and sparse, but as they grow, they become more effective at interacting with radiation, both absorbing and scattering light from the star. Once dust grains reach sufficient size and abundance, radiation pressure on them can become an important driver of the outward acceleration of the gas. Thus, the extended atmosphere is the zone where gas transitions from being primarily influenced by internal motions and gravity to being influenced increasingly by radiation pressure on dust and by the global structure of the wind. In Antares, evidence for dust in the inner regions of the envelope suggests that at least some dust formation occurs relatively close to the star within a few stellar radii of the photosphere, although the exact locations and efficiencies of this process are still uncertain. These uncertainties highlight that despite detailed observations, the physics of red supergiant atmospheres remains an active field of research, with ongoing efforts to understand how convection, pulsation radiation, and chemistry combine to produce the observed structures. From a broader descriptive perspective, the extended atmosphere of Antares can be thought of as a thick, complex shell of gas that blurs the boundary between star and space. It is neither as dense and opaque as the deeper interior, nor as tenuous and free-flowing as the outer circumstellar envelope. Instead, it occupies an intermediate regime where material is loosely tethered to the star, moving in response to internal forces and radiation, but not yet fully committed to escape. At this stage of the inward journey, attention remains on this extended, molecularly rich atmosphere as the immediate environment surrounding the photosphere, a region that both records the effects of processes deeper within and prepares material for the transition into the stellar wind that shapes the larger circumstellar envelope. At the level of the photosphere, Antares A presents what may be called its visible surface, the layer from which most of its optical light escapes into space. Yet even this surface is not a simple uniform shell, but a complex, slowly changing pattern of bright and dark regions shaped by convection, atmospheric structure, and the star's overall geometry. In a basic sense, the photosphere is defined as the depth at which the gas becomes transparent enough that photons can travel outward without being scattered or absorbed many times, and for a red supergiant like Antares, this depth lies in a cool, low-density regime compared with the dense interior. The effective temperature at this level is only a few thousand degrees above absolute zero, which is low by stellar standards, and explains the deep orange-red colour seen from Earth. Because cooler gas emits more strongly at longer wavelengths, the light from Antares peaks at red and infrared wavelengths, and even after allowing for modest reddening by interstellar dust, the star appears distinctly warm in colour when compared with the bluish or white stars nearby in Scorpius. The apparent shape of the photosphere on the sky is that of a slightly flattened disk, rather than a point as revealed by interferometric measurements that resolve its angular diameter. Across this disk, the brightness is not constant. Like many stars, Antares shows limb darkening, a gradual decrease in intensity from the center of the disk toward the edge, caused by the fact that lines of sight near the limb pass through cooler, more rarefied layers of the atmosphere compared with lines of sight toward the center. In red supergiants, this effect can be modified by the presence of an extended atmosphere and molecular layers above the photosphere, so that the detailed limb shape may deviate from simple models. Nevertheless, the general tendency for the edges to appear dimmer than the center holds, giving the star a softly rounded brightness profile. Superimposed on this smooth gradient are irregular patterns of brighter and darker patches that trace the influence of convection and other large-scale motions. In the Sun, convection manifests at the surface as a fine granulation pattern made up of many small cells. In Antares, with its much larger radius and lower surface gravity, convection operates on much larger scales. The cells can span a substantial fraction of the visible disk, with hot rising material in the centers and cooler sinking material in the lanes between them. Where hotter gas rises, the photosphere can appear slightly brighter and perhaps somewhat hotter. Where cooler gas sinks, it can appear darker. Interferometric images of Antares reconstructed from high-resolution data show evidence for such giant cells in the form of bright regions offset from the center, and darker patches on the opposite side indicating that the surface is mottled. These structures change over time as convection patterns evolve, gas flows shift, and energy transport reorganizes itself in the outer layers. Because the convective cells in a red supergiant are so large, their lifetimes can be long, compared with the small granules on the Sun, yet they are not permanent. Over intervals of months to years, the arrangement of bright and dark patches can shift, producing subtle changes in the star's apparent shape and brightness distribution. These surface structures contribute to the irregular variability of Antares. Photometric observations over many years show that the star's brightness varies by small amounts on timescales of several hundred days, and also on shorter and longer timescales. There is no single strictly repeating period, but rather a superposition of quasi-periodic and more random components. This behavior is typical of many red supergiants, and is thought to arise from the combined effects of convection, radial pulsations, and changes in the extended atmosphere. When large convective cells rearrange when the outer layers expand and contract slightly, or when opacity in molecular layers changes, the total light output in the visible band can rise or fall by fractions of a magnitude. To the unaided eye, these changes are subtle, and usually not noticed during casual viewing, since the star remains one of the brighter points in the sky. Careful monitoring with instruments, however, reveals a pattern of slow, gentle fluctuations rather than strict constancy. The photosphere of Antares is also affected by the molecular layers above it. In certain wavelength bands where molecular absorption is strong, the effective radius of the star increases because photons at those wavelengths originate from higher, cooler layers. This can give the impression that the star's size depends on the color in which it is observed. In practice, measurements at different wavelengths show that Antares appears larger in bands dominated by molecular features, and smaller in continuum bands where absorption is weaker. This reinforces the idea that the photosphere is not a rigid boundary, but a depth that depends on wavelength and viewing direction. In directions where molecular opacity is enhanced, the emergent light may trace higher layers. In directions where convection has brought up hotter gas and reduced molecular abundance, the photosphere can be sampled deeper. The rotation of Antares adds another dimension to the surface behavior, even though the projected rotation rate at the photosphere appears to be slow compared with that of some smaller stars. In a star as large as a red supergiant, even a slow rotation can correspond to a significant linear speed at the equator, but the long rotation period and the thick convective envelope mean that rotation is deeply entangled with convection, rather than imposing a simple, rigid pattern. The net effect may be to introduce gentle asymmetries and to help organize some flows, but the evidence suggests that convection remains the dominant driver of surface structure rather than rotation. The gravitational field at the photosphere is weak compared with that at the surface of a compact star. This low surface gravity allows the atmosphere to extend and to be easily perturbed by internal motions. Gas lifted by convection can reach heights of several stellar radii before cooling and either falling back or joining the outflow. From the perspective of an observer looking at the photosphere, this means that the surface is continuously exchanging matter with the layers above and below. Hot gas bubbles up, radiates energy and cools. Cooler gas sinks back toward deeper regions. This perpetual turnover helps transport energy from the interior to the surface, where it is radiated away, and also seeds the atmosphere with the irregularities that later grow into clumps in the wind. Despite the underlying complexity, the photosphere retains a degree of stability when viewed at the coarse scale of human perception. The star does not suddenly change shape or color in an obvious way. The overall orange-red hue, the approximate brightness, and the position in Scorpius persist night after night across many seasons. On closer inspection, though, the surface is far from static. Each bright patch and darker region marks the outcome of flows and temperature variations, driven by conditions deeper within the star. In some epochs, a particular hemisphere may appear brighter, because a large convective cell sits near the center of the visible disk. At other times, different patterns emerge. These changes influence not only the total flux, but also the detailed shape of spectral lines, which can appear shifted or broadened in ways that reflect motions in the photospheric gas. By studying these subtle signatures, astronomers gain insight into the scale and speed of motions at the surface. The photosphere also serves as the starting point for the emergent spectrum that encodes information about chemical composition. The absorption lines seen in the light from Antares arise mainly in the photosphere and in the layers immediately above it, where atoms and molecules imprint characteristic patterns on the continuum radiation. These lines show that the atmosphere contains elements heavier than hydrogen and helium, some of which have been brought to the surface from deeper layers by convection and internal mixing processes. While detailed abundance analyses require careful modelling, the overall picture is that Antares, like other evolved massive stars, displays signs of processed material at its surface, a reflection of nuclear reactions in its interior and of the circulation of material within the star. At the present stage of the inward journey, however, the emphasis remains on the emergent light and the surface patterns rather than on the deeper nuclear processes themselves. From a descriptive standpoint, the photosphere of Antares can be seen as a broad, gently darkened disk, riddled with slowly shifting bright and dark regions glowing in orange-red light, and changing its output in a calm, irregular rhythm over long intervals. This surface marks the interface where energy transported from the deep interior finally escapes into space. Beneath it lie layers where the energy is generated and where different modes of transport govern how that energy moves outward, layers that will form the focus of the next step inward beyond the visible surface and into the interior structure of the star. Beneath the mottled photosphere of Antares A, the outer layers that observers see merge into a vast interior where temperature and density rise steadily inward, and where nuclear fusion in multiple shells provides the energy that ultimately emerges as the star's luminous orange-red glow. In broad terms, the structure resembles a series of nested regions, each with its own physical conditions and role in transporting energy from deeper zones toward the surface. In the extended envelope above the photosphere, energy moves mainly by convection, with large volumes of gas rising and sinking as they carry heat outward. Just below the photosphere, this convective pattern continues with eddies that are far larger than granules on the Sun, but governed by the same basic physics. Hot gas becomes buoyant, rises, radiates some of its energy away, cools, and eventually sinks back down. Because the surface gravity of Antares is low and its radius is enormous, the convective envelope occupies a substantial fraction of the total volume of the star. Within this envelope, temperatures and densities are high enough that hydrogen remains ionized and the gas behaves as a hot plasma, yet they are still modest compared with the deeper regions where nuclear fusion operates most intensely. As one moves inward in thought from the photosphere through this convective envelope, the pressure grows as the weight of the overlying layers increases. Temperatures climb from a few thousand degrees at the surface to tens of thousands and then to hundreds of thousands of degrees deeper in. In these inner parts of the envelope, energy produced in the core and in interior burning shells has already been partially processed, but still consists largely of photons that scatter many times off electrons and ions, and of the mechanical energy of convective motions. The opacity of the plasma, set by the abundance of electrons and ions and by the presence of heavier elements, determines how easily radiation can move. Where opacity is high, radiation is trapped, and convection becomes the more efficient means of transport. Where opacity drops, radiation can carry energy more directly. In a massive red supergiant like Antares, theoretical models indicate that much of the extended envelope is convective, meaning that large-scale motions dominate energy transport. Deeper in there may be regions where radiative transport becomes more important again, depending on the detailed stratification of composition and temperature. In these zones, photons diffuse outward through this plasma without significant large-scale bulk motion of the gas, following a path that is random at the microscopic level, but ordered at the macroscopic scale as a gradient of energy from hot inner regions to cooler outer ones. At still greater depths below the base of the convective envelope lie shells, where nuclear fusion continues in layers surrounding a more compact central region. Antares began its life as a hot massive star fusing hydrogen into helium in its core. As that central hydrogen supply became exhausted, the core contracted and heated while the outer layers expanded and cooled, leading to the red supergiant phase. In this state, hydrogen fusion no longer occurs primarily in the core, but in a shell surrounding an inert or differently burning inner region. The hydrogen-burning shell sits at a radius where temperatures and densities remain high enough for hydrogen nuclei to overcome their mutual repulsion and fuse into helium, releasing energy in the process. This shell is thin in radial extent compared with the size of the envelope, but it encircles the entire inner core like a glowing band, continuously adding helium ash to the region beneath it and providing a significant fraction of the star's luminosity. The energy released in this shell flows both inward and outward, contributing to the heating of the core and to the expansion of the envelope. Outside the hydrogen-burning shell, the gas is enriched compared with its original composition, because some material has been processed and mixed, yet it no longer sustains steady fusion. Instead, it acts as part of the envelope, responding to the energy flowing through it. Inside the hydrogen shell, the growing reservoir of helium and heavier elements forms the core and its surrounding zones, where further stages of fusion may occur depending on the current state of the star. In a star with a mass in the range inferred for Antares models, predict that helium has already begun, or will soon begin to fuse into heavier elements in deeper layers, if it has not done so already, and that additional shells of burning can develop over time, such as helium, burning in a shell around a carbon and oxygen core, and perhaps further shells at higher temperatures. However, the exact configuration at any given moment is uncertain, because observations cannot directly probe these inner regions, and models must account for factors like rotation, internal mixing, and mass loss that are not fully constrained. What can be said confidently is that Antares as a red supergiant possesses an interior in which nuclear fusion is stratified into shells, with hydrogen burning in a shell outside a more processed inner region, and with energy from these reactions driving both the luminosity and the extended structure of the star. The presence of burning shells affects the mechanical balance of the star. The energy released in these narrow regions exerts pressure that helps support the overlying envelope against gravity. As fusion adds helium and heavier elements to the core, the inner regions contract and heat, potentially igniting new burning stages while the envelope responds by adjusting its radius and temperature. This interplay between core contraction and shell burning shapes the long-term evolution of the star during the red supergiant phase, including changes in luminosity and radius that occur over time scales much longer than human lifetimes. Inside the burning shells, where temperatures and densities become still higher, energy transport tends to be more radiative because the plasma is so hot and ionized that photons can carry energy efficiently despite the high densities. In these deep zones, photons are born with very high energies, but gradually lose energy as they scatter and are absorbed and re-emitted countless times on their way outward. The path any given photon takes is random, but in aggregate the flow is from hot to cool, sustaining a steady outward luminosity that is nearly constant with radius inside the fusion region. The fusion shells themselves sit at positions where the balance between temperature density and composition allows particular nuclear reactions to proceed at significant rates. Small changes in temperature can lead to large changes in reaction rates, so the structure of these shells is self-regulating. If the shell becomes too hot and expands, the density drops and the reaction rate decreases, reducing the energy output and allowing gravity to compress the shell again. If the shell cools and contracts, the density and temperature rise, increasing the reaction rate and providing more energy to oppose further contraction. This feedback maintains approximate stability over the timescales characteristic of the red supergiant phase, although on longer timescales the gradual depletion of fuel and accumulation of heavier elements lead to slow structural adjustments. The chemical composition of the interior bears witness to the history of these processes. Deep inside material has been processed by multiple stages of fusion, transforming hydrogen into helium into heavier elements such as carbon and oxygen, and later in the evolution of massive stars into even heavier nuclei. Some of this processed material is brought closer to the surface by convection, and by mixing processes that transport elements from the inner regions outward. The altered abundances detected in the photosphere and extended atmosphere, such as enhanced helium and certain heavier elements compared with the initial composition, therefore reflect the work of the burning shells and the interior mixing over millions of years. Yet the detailed distribution of elements in the deepest layers remains hidden from direct observation, accessible only through theoretical models that must be consistent with the star's current luminosity, temperature, and mass, as well as with general knowledge of massive star evolution. From a descriptive standpoint, the interior of Antares, between the visible surface and the central core, can be seen as a layered dynamic structure. A vast convective envelope transports energy through rising and sinking motions sitting above one or more narrow shells, where nuclear fusion continues to convert lighter elements into heavier ones, and below that lies an even hotter, denser region, where fusion products accumulate. Energy generated in the burning shells and in deeper zones flows outward through this stratified interior, changing form many times, but always moving from regions of higher temperature to regions of lower temperature, until it finally emerges at the photosphere as the light that makes Antares such a prominent star in the night sky. At this stage of the inward journey, attention rests on these shells and transport layers as the middle structure of the star, linking the complex convective outer envelope to the more extreme conditions in the central core, which lie still deeper within and which govern the ultimate internal state of Antares A. Deep inside Antares, far beneath the vast convective envelope and the hydrogen-burning shell, lies the core, a compact region where temperatures and densities reach some of the highest values found inside any star visible to the naked eye, and where advanced stages of nuclear fusion proceed in layered zones that cannot be observed directly, but are inferred from models of massive star evolution consistent with the star's present red supergiant state. In this central region, matter is compressed to densities far above those in the overlying shells, and temperatures rise to values of many hundreds of millions of degrees high enough that helium and heavier nuclei can collide with sufficient energy to overcome their mutual repulsion and fuse into still heavier elements. The core does not occupy a large fraction of the star's radius, but it contains a significant portion of the total mass wrapped in layers, where different fusion reactions operate in narrow stratified zones. After the phase in which hydrogen fuses to helium in the core, the central hydrogen supply becomes depleted, and hydrogen burning moves into a shell surrounding a core that is now dominated by helium and heavier elements. As the core contracts under gravity, it heats until helium fusion ignites in the central regions, primarily through a chain of reactions in which 3 helium nuclei combine to form carbon, and in which carbon can capture additional helium to form oxygen. In such a helium-burning core, energy is released at a high rate, and the resulting carbon and oxygen accumulate in the innermost layers, while fresh helium from the surrounding region is consumed in a relatively thin burning zone. The structure is not static. As helium is used up in the very center, the region that actively burns helium can shift outward, forming a shell around a core that is now rich in carbon and oxygen, while hydrogen continues to burn in a shell still farther out. The result is an interior that even at this stage already exhibits a layered arrangement with hydrogen burning above helium burning, and with a central region composed mainly of fusion products. In more advanced stages, as the core contracts and heats, further additional burning shells can ignite in high-mass stars including carbon, burning neon, burning oxygen burning, and eventually silicon burning in successive inner zones. Each of these stages operates at progressively higher temperatures and densities, and on progressively shorter timescales. While hydrogen burning in the main sequence phase can last for many millions of years, helium burning persists for a shorter fraction of that time, and the later burning stages can proceed over intervals that shrink from hundreds of thousands of years down to years or even shorter durations for the final most extreme phases. For a star with a mass in the broad range inferred for Antares models suggests that it either has already entered some of these advanced burning stages or will do so after its current red supergiant phase. But the precise combination of shells and their detailed locations at the present time are not directly measurable and remain subject to model-dependent uncertainties. What is well established from the general theory of massive stars is that each burning stage contributes less and less to the observable luminosity compared with the energy carried away by neutrinos, nearly massless particles that interact only weakly with matter. In the deep core where advanced fusion occurs, the high temperatures favour reactions that produce copious neutrinos, which stream outward almost unhindered, carrying energy directly out of the star without contributing significantly to heating the overlying layers. As a result, even though the nuclear power generated in the core grows enormous during the most advanced burning stages, much of that power leaves invisibly as neutrino emission rather than as light, and the luminosity seen at the surface does not increase in proportion. This neutrino cooling plays a central role in regulating the core's temperature and structure, allowing it to contract and heat in steps between burning stages, while the outer envelope remains in a comparatively steady, red supergiant configuration on human timescales. The matter in the deepest part of the core experiences pressures so high that electrons are forced into states where quantum mechanical effects become important in supporting the gas against gravity. In such conditions, electron degeneracy pressure can contribute significantly to the resistance against further compression alongside the thermal pressure of the hot plasma, and in earlier stages the pressure of radiation, as heavier nuclei accumulate, particularly elements in the ion group that represent the endpoint of energy-producing fusion. The balance between gravity and these internal pressures becomes increasingly delicate. Fusion reactions involving nuclei lighter than the ion group can release energy by combining them into heavier nuclei, but once nuclei reach the ion group, further fusion or fission no longer yields net energy. Instead, such reactions would consume energy, so fusion-powered support cannot continue indefinitely in the same way once the core composition becomes dominated by these elements. In the evolutionary path of a massive star, this leads to the buildup of an inner core of ion group nuclei surrounded by shells where lighter elements still fuse, while the core's ability to respond to further contraction by producing additional energy diminishes. For Antares, the exact extent to which an iron-rich core has formed and the detailed distribution of elements in the deepest layers depend on how far the star has progressed along this path, which is not directly observable at present, and must be inferred from its mass, luminosity, effective temperature, and the general timelines for stars of similar mass. Even without precise knowledge of the current composition, the basic structure of the advanced core can be described as an arrangement of concentric zones, an innermost region made of the most heavily processed material, produced so far surrounded by shells, where successively lighter elements are still undergoing fusion, all enclosed by the broader, convective and radiative layers that transport energy outward. Within each burning shell, nuclear reactions occur at rates exquisitely sensitive to temperature. A small change in temperature can lead to a large change in reaction rate, which in turn alters the local energy production. This feedback helps maintain a quasi-steady balance in each shell, because any tendency toward overheating causes expansion and cooling, which lower the reaction rates, while any tendency toward underheating leads to contraction and reheating. In the advanced stages, however, the efficiency of neutrino cooling and the rapid consumption of fuel mean that these balances can be maintained only for relatively short periods before the composition and structure change again. Throughout these processes, the interior of Antares remains in hydrostatic equilibrium on average, with the inward pull of gravity balanced by the outward push of pressure at each radius. The density and temperature profiles adjust. Shells turn on and off or move outward as fuel is consumed, and the core slowly grows in mass and changes in composition. The envelope above responds by adjusting its radius and temperature only gradually compared with the rapid changes in burning conditions deep inside, so that, from the outside, Antares continues to present a relatively stable red supergiant appearance, even while its core experiences increasingly advanced fusion stages. The energy generated in the core and in the surrounding burning shells flows outward through the radiative and convective layers, until it reaches the photosphere where it escapes as the light that gives Antares its brightness in the sky. At this level of the inward journey, the focus rests on the present internal arrangement of fusion shells, the build-up of heavier elements in the core, and the way neutrino cooling and stratified burning shape the star's internal state, without yet turning to the external consequences that will eventually follow from this structure on longer timescales. In the innermost regions of Antares A, the advanced burning shells and the dense core together define not only the star's present internal state, but also its eventual fate, because the sequence of nuclear reactions and structural changes underway there leads in time to conditions under which the core can no longer support itself, and a core collapse supernova becomes unavoidable according to current models of massive star evolution. As the star continues through its advanced stages, helium, carbon, oxygen, and other elements fuse in stratified shells, and each burning phase leaves behind a growing central region composed of heavier nuclei. In this central region, elements in the iron group accumulate because fusion processes that build nuclei up to this group release energy, while further fusion beyond this point does not provide additional energy to counter gravity. With each stage of burning, the core contracts slightly and heats while the outer envelope remains extended and cool, supported by the energy produced in the shells. The core at this stage is extremely dense, with nuclei packed closely together and electrons forming a degenerate gas that contributes significantly to the pressure resisting further compression. The balance between gravity pulling inward and these internal pressures pushing outward remains stable for a time, but as nuclear fuels in the shells are exhausted, and as the core composition shifts toward heavier elements, especially iron group nuclei, this balance becomes increasingly delicate. The rate at which this evolution proceeds depends on the mass of the core, the efficiency of mixing the neutrino emission rate and other factors, and current understanding places Antares somewhere along this sequence without precisely fixing its exact stage. What is clear from models of stars with comparable mass is that once a sufficiently massive iron-rich core has formed, no further fusion reaction can generate enough energy to support it. At that point, the interior reaches a threshold where the inward pull of gravity overwhelms the pressure provided by electrons and thermal motions, and the core begins to collapse. During the early part of this collapse, densities and temperatures rise rapidly. Electrons are captured by protons in the nuclei, producing neutrons and neutrinos. These neutrinos stream outward, carrying away energy and reducing the pressure support even further. The collapse accelerates as the core contracts to nuclear densities, at which point the strong nuclear force and the degeneracy pressure of neutrons halt the collapse of the innermost part, almost abruptly creating a very stiff, dense core, composed mainly of neutrons. The infalling outer core material then impacts this newly formed neutron-rich core and rebounds, sending a shock wave outward into the overlying layers. In simple terms, this marks the transition from a collapsing core to a developing supernova explosion, although the detailed physics of how the shock is revived and how it ultimately expels the stellar envelope involves complex processes that are still under active study, including the interaction of the shock with the intense neutrino flux. The shock wave emerging from the core moves outward through the inner regions of the star, heating and compressing material as it goes. As it travels through the shells of different elements, it triggers explosive burning that produces additional heavy nuclei and alters the composition of the ejected material. At the same time, the vast number of neutrinos emitted from the collapsing core interact with the layers just above, depositing energy and helping to revive and sustain the outward moving shock. If sufficient energy is transferred to the envelope, the shock continues outward and eventually reaches the outer layers of the star, accelerating them to high velocities. When this happens, the envelope is blown off into space, and the star as seen from outside brightens dramatically, becoming a supernova that for a time can shine with a luminosity comparable to that of an entire galaxy. For Antares, if and when this event occurs, the outward appearance in the sky would change from that of a bright red supergiant to that of a transient supernova, although current models place the expected time until such a collapse somewhere in a broad range extending from hundreds of thousands to around 1,000,000 years, and observations today do not indicate any immediate approach to that final stage. The timescales here are long compared with human history, and no method currently available can predict a precise date or even a narrow range for the eventual explosion. After the shock-driven ejection of the envelope, the core remnant is left behind as a compact object. For a star whose initial mass lies within the range inferred for Antares, theoretical calculations suggest that the core remnant is likely to be a neutron star if the core mass at collapse remains below a certain limit, or possibly a black hole if the core is more massive and the collapse cannot be halted by neutron degeneracy pressure. The exact outcome depends on details such as mass loss prior to collapse rotation and the efficiency of neutrino-driven processes during the explosion. In either case, the remnant would be extremely compact and dense, with a radius of only a few tens of kilometers for a neutron star or a smaller event horizon radius for a black hole containing a mass comparable to or greater than that of the Sun. The envelope material ejected by the explosion would expand into the surrounding interstellar medium as a supernova, remnant a shell of gas and dust enriched with heavy elements, produced both before and during the explosion. This expanding shell would interact with the ambient gas in the upper Scorpius region and in the broader Scorpius-Centaurus environment, driving shocks into the interstellar medium, compressing nearby clouds, and perhaps contributing to future episodes of star formation. Over tens of thousands of years, the remnant would grow and fade its initial bright emission, giving way to a more diffuse and fainter shell as it cooled and mixed with the surrounding gas. The heavy elements carried outward by the ejector would eventually become part of the general interstellar reservoir from which new stars and planets form. In this way, the core collapse of a single massive star like Antares A plays a role in enriching the galaxy with elements heavier than helium, important for the chemistry of future generations of systems. From the perspective of the star's internal evolution, however, the important point at this stage is that the core is heading toward a configuration in which such a collapse will occur once certain mass and composition thresholds are reached, even though the exact timing remains uncertain and distant on human timescales. Throughout the remaining red supergiant phase, the core continues to adjust as burning shells change and as neutrino cooling and contraction proceed. The envelope above, including the extended atmosphere circumstellar envelope and dusty outflow, responds to the gradual changes in luminosity and mass. But these responses are slow and do not announce the imminent arrival of collapse long in advance in any way that current observations can clearly detect. The star remains on the outside, a bright variable red supergiant in the heart of Scorpius, while inside the advanced fusion and the build-up of heavy elements move it step by step along a path defined by the physics of massive stars. For now, Antares A is observed in this red supergiant state, with its core undergoing advanced burning and its fate set by the eventual exhaustion of nuclear options for supporting the innermost region. The core collapse and supernova that follow in models of such stars are part of that defined path, but they belong to future stages in the life of Antares that lie far beyond present human experience, even as the internal conditions that will one day make them possible are already in place in the dense hot heart of the star.